Hello, everyone. Welcome to a more technical talk. So first of all, I wanted to ask a question and see who in the room, so hands up in the air, who in the room loves cooking? Hands in the air. All right. So that has nothing to do at all with the talk, but I want to start with an interactive element to get you warmed up. So now we get into the boring bits. I'll talk today about a few concepts, but I want to start off with telling you what I will not be talking about. So this will not be about infrastructure performance, like how to set up your Kubernetes clusters and things like that. It will not be about front-end performance, how to lazy load your images and similar things. And it will also not be about network performance, how to reduce the latency in your DNS round trips or something like that. So these are the things that we will not cover. However, we will cover some things. So everything I'm talking about is meant to be back-end only. So we're not talking about front-end performance, which is a huge topic, of course, but it's not about this talk now. And this is either algorithmic in nature, so we're changing our approach of doing the solution that we need for our problem, or implementational, meaning that with the given approach that we have, we try to make it faster or cheaper to execute. So, first of all, the talk has a pretty long title, and it contains performance and scalability. So let me talk about these two terms, because oftentimes these are confused, or people think they are the same thing, or they are not clear what the difference is. So let me first go over that. The performance is how fast you do a single unit of work. And making something more performant means, for a given type of work, you just aim to execute it faster, so that it takes less time to execute. And scalability is the ability of your system, of your application, to easily support a high load, a high usage, without degrading in performance. And while these two are directly related, they are not the same, and oftentimes optimizing for one degrades the other. So if you have a system that does something a very high amount of times, and you improve the performance, then it will in total take a lot less time. But if you multiply that at internet scale, it might mean that that time that it takes is still too much time. And with the finite resources of the servers that you have, it might just mean that your servers just crash. So scalability is not necessarily making it faster. Oftentimes, it's actually making it slower, but it changes the approach of how it's done so that it can more easily be done multiple times at the same in the same request. For example, it can be parallelized. You can do only a fraction of the work and try to guess the rest and things like that. So performance and scalability are not the same thing, and sometimes optimizing for one degrades the other. So with that being said, how can we visualize that relationship? We have a diagram here, a canvas with two axes, one being how fast or slow a given operation is, and the other is about the distribution of our load. So at the left, we start with a very low load. A single visitor, our grandma does a request on our private blog. It's a single request, the blog does not do much, and if we optimize it for performance, this will actually be very fast. So we can ensure that this single operation executes almost instantly, and we're good to go. However, if now all of a sudden our blog is shared by an Instagrammer, by an influencer, what happens is that if our blog is not scalable, the performance will slowly degrade the more usage our blog gets. And with high load, it might even end up not being able to serve these requests at all anymore, because our server just crashes under the high load. And with a scalable approach, first of all, it might actually be slower to do a single request, because usually for a scalable approach we have much more logic. It is not the simplistic way of doing it as fast as possible, but there's way much more involved. We have heuristics to decide when do we do it at all, maybe we only do it every 10th step, and so on and so forth. So we have much more logic, making it slower, but as the load increases, we are able to still serve these requests. The degradation is either non-existent or most of the time happens in such a way that we still can serve these requests over the entire spectrum of the load that we need to serve. So that is the relationship between performance and scalability. That's a very important distinction, and some of the mechanisms I'm talking about, some of the concepts, they improve the performance and others improve the scalability. So with that being said, first of all, if you think that something is too slow, measure it. Figure out, is it actually slow or is it just perceived? How slow is it? Measuring is important to pinpoint problems and to have a frame of reference so that if you make changes, you can actually find out if you made an improvement or if you maybe added a regression. So with measuring, you can find the hotspots so that you can focus your work on where it matters most, because optimization is costly, it's time-consuming, so you don't want to optimize something that is never used at all. You want to optimize the one point that has the highest impact on your bad performance. You optimize against requirements, so optimization is also always a trade-off. I'm probably standing in front of the slides here, so sorry about that. Optimization is always a trade-off. So meaning that you don't optimize indiscriminately, you figure out what your business requirements are, what is the core thing you need to achieve as best as possible, and you optimize for that. That might mean making something else slower. It's always a trade-off. And then finally, measuring in itself has an effect on your platform. So the more tools you add to measure what is happening, the slower your platform becomes as well, because you add the overhead of measuring on top of everything else. That is why it's important to always use adapted tools. You can use tools that give you very, very precise measurements about what your code is doing, but you wouldn't run that on a production server. The production server will just crawl to a halt. So that's why there's 3 general categories of tools that you'd need for measuring performance and scalability. Profiling is the act of running your code through a measurement system where every single line of code is being measured and is being analyzed on its impact. So with a profile, you can see, okay, my code spends most time in this function, it uses that much memory, it has so many calls of this function, and so on and so forth. Then we have benchmarking, which basically takes a function or subsystem and tries to execute it multiple times and then fetches average times to measure it. This serves a different purpose because some code, for example, will not run with the same performance on every iteration. So getting average numbers is something else than profiling the actual code. And then finally, we have load testing. And load testing is trying to figure out how scalable your system actually is by using it from the outside, by just hitting it with as much actual load as you can and see where it breaks. Because actually, pretty much every system will break if you put enough load on it, if you put enough stress on it. So those are the 3 main ways of how you measure both performance and scalability. And whenever you measure something, keep in mind that measuring itself has an impact as well. For the WordPress system, for example, it is common to use Query Monitor to get insights into your code. But remember that using Query Monitor makes the code slower. So it is the measurements that you get give you a relative measurement of how your code relates to a different version of the code. But the absolute numbers don't mean anything because the absolute numbers will be completely different as soon as you switch Query Monitor off Always keep that in mind. So, I will now talk about a lot of higher level concepts, and sometimes there's PHP code as well, but this talk will not include that much PHP code. Even though it's in the title that it's a PHP talk, it's more about the server side of the application, meaning PHP in WordPress. So one of the main concepts you should be aware of when you think about optimizing your application, optimizing your code, is that there is a degree of how real-time your code happens to be. I invented a few terms for this talk, so hopefully you don't mind that. Here I came up with the recency spectrum. So on the left, we have what is pure dynamic code. So that is the default mode of WordPress to operate. You have a template that is being executed every time you do a web request. So if someone clicks a link in the browser, and you just have a default WordPress installation, every single time WordPress will go through an entire cycle of dynamically generating that result. Then, as we move further towards static code, we add interruptions into the real-time cycle. So if we talk about micro-caching, for example, micro-caching is the fact of doing near real-time. For example, if you do a news page with live ticker and things like that, you want it to be pretty much real-time, but actual real-time is too hard on the resources. So micro-caching would mean you cache it for 5 seconds, for example. 5 seconds delay for most people is still real-time. A lot of people even take longer to even download your web page if you add enough ads to it. So 5 seconds is nothing in terms of the recency, in terms of how real-time it feels, but 5 seconds in terms of server resources. If you're getting millions of page requests per second, 5 seconds is a huge savings potential for your server. So adding that type of micro-caching still feels like real-time, but is way more scalable than just being dynamic. Then we have regular caching. That usually means you decide which parts of your site should have which time to live. So this should be cached for 30 minutes. This should be cached for 2 days, and so on and so forth. And then every time something that was cached expires, it gets regenerated. So you have control over how long you want the different subcomponents of your page to be cached. That goes beyond micro-caching, so it serves even more, and it saves even more server resources. But this is not real-time anymore. So if you have one part that is cached for a week, well, you will not get updates for weeks. You can hardly say that feels like real-time then. And then we have long-lasting caches, with the main difference being that it does not directly have a time to live. Usually the time to live is very high, or it doesn't expire at all, and you have a trigger that invalidates the cache instead. For example, you can have a cache that stores how your post is rendered, and only when you save an update to your post, the cache will get invalidated. For the rest of time, as long as nobody changes that post, you don't need to regenerate the cache. It is still current. It doesn't grow stale over time just because of it. As long as nobody changes the post, it will stay current. And then finally, at the other end of the spectrum, we have static code. So that means there is no runtime way of updating the representation. This is something like a static site generator, where the entire rendering is changed from being during runtime to being during compile time or during deployment. So that is, as long as you don't deploy a new version of your code, it is static. So this is the recency spectrum. Feel free to use that term if you like it. I don't know if it exists. I didn't find it, but it made sense to me. So with that said, as we saw that the more caching we add, the more server resources we save, way up to being static at the end, the obvious approach is cache all the things. But also curse all the caches, because everybody who has ever dealt with caches knows that, yeah, these things can really be a pain to debug. So, yeah, you should always be aware that, as I already said before, everything is a trade-off. And it is not only a trade-off in terms of performance versus scalability. It's also a trade-off between how optimized it is and how maintenance heavy it is. We have different types of caches that come into play when we work on a PHP application server. The most PHP one of them is the opcode cache. So the opcode cache is the cache that is used by the PHP runtime itself to store the results of the PHP compiler. It's not technically a real compiler, but let's stick with that for simplicity's sake. So when you execute a PHP file, the PHP file is loaded from a file system, it is lexed, it is parsed, it is compiled into bytecode. That bytecode is then processed, and that is then generating your result. And the opcode cache, it actually caches the result of some of these steps. We'll go into that into more detail a bit later. Then we have a server-side data cache. I don't know if that is a technical term. Basically, everything you use in your custom code, where you store something, hopefully not in the options database, in your Redis cache and things like that. That is just pure data that you store. What that data represents might be very different things. It might be the generated HTML. It might be information about the user that you retrieved from an API, whatever. And then we have the browser-side cache, which is the cache that the user of your site has on their end. And the browser-side cache is that is the most front-end we'll get here, but basically everything you can have end up in the browser cache means your server is not being hit anymore. So that is a way of not doing the work, which is way faster than doing it in a cheap way. So let's talk about cache expiry. As I already said, with some of the ways you can cache, you need to define what the time to live is, how the cache behaves when it is invalidated. And cache invalidation is the important bit. That is the thing that is hard to get right and that makes all the difference. Because caches are perfectly fine if your cache invalidation is perfectly fine. If you have an issue with your cache invalidation, then you get random output and you don't know where to start to debug. So cache invalidation is very important to get right. The most simplistic way of dealing with cache expiry is a hard time to live. It basically means you cache something for, let's say, 10 minutes. So during these 10 minutes, the first time you generate the result, and then it is cached, it's stored in the cache, and then for 10 minutes, we always serve it from the cache. And then after these 10 minutes, our cache is expired. So the next request figures out, oh, the cache is expired, I cannot use that. So it goes and regenerates the result, stores that back into the cache, and then serves that cached result again. That is the most basic form of caching, and it is easy to implement, but it comes with a few drawbacks. So usually, you can imagine that most of the time, you use a cache for an operation that's expensive to do. So if you now have a hard TTL and your cache expires, the user requested the result, but you don't have the result, it's stale. So you need to regenerate it. But it was an expensive operation, so it takes a long time to regenerate it. And all the while, the user is still waiting to actually get that result. That's why a hard TTL, it's easy to implement, but oftentimes it's just not a good experience because you have a synchronous lock on the user until the result is regenerated again once it expired. So what is an improvement on that is a soft TTL. You cannot always use a soft TTL, but when you can, you should always prefer that. It basically means that once you figure out that your cache has expired, instead of letting the user wait, you continue to serve the stale result of the cache. So you don't erase the cache results. You can continue to serve the stale result, but you trigger a background process to update the cache in the meantime. And you might still serve thousands of users while this regeneration happens. They just get stale content out of the cache, which in some instances is perfectly fine. And then when the cache is being updated, then you replace the stale version with a new updated version. So that is always preferable. It's not always usable. It depends on whether the result you request needs to be precisely accurate or whether it needs to be good enough. It needs to be just, if you have, let's get back to the news cycle, for example. If you continue to serve the last version of the live ticker for 2 more seconds, that's not a big deal. But if you answer an authentication request with a stale result, that might be more problematic, of course. And then finally, we have expiry via cache key. Whenever you cache something, you use a key to reference that part in the cache. And you can actually use the cache key, when you generate the cache key, you can use the data point that defines whether your data is fresh or stale. You can include that data point into the cache key. So when there's a reason for your data to be stale, your cache key will change and you will have a cache miss. And that will force the cache to be regenerated without you needing to manually adapt it. So this makes your cache reactive in a form where some outside source can actually have an effect on your cache key, which creates a cache miss, and therefore automatically the cache is invalidated. You can only use this when you use a cache storage that cleans up after itself automatically, though. So don't do that with the WordPress options database, for example, because it will just fill up after each cache miss, and as the cache key changes automatically, you have no way of manually going in and cleaning up the old entries. That's an important distinction. So the act of caching can be done in a hierarchical way. And oftentimes this is referred to as Russian doll caching. You know, these dolls where there's one inside of another, inside of another. And you don't see the inside dolls as long as you don't open up the outside doll. And what Russian doll caching is if you have a given result, let's say our home page, we might have full page caching, which caches the entire result. That's fine. But now if, let's say, okay, which one did I pick now for the slides? I think I picked headline B. Let's say headline B needs to update. The simplistic way of doing that is just scrapping our page cache and regenerating the entire page. So with Russian doll caching, we can actually have a hierarchy of caching in place with different cache keys. These cache keys can use the expiry via cache key, by the way, which is a very smart way of combining Russian doll caching with an automated optimization. And then if now we want to update headline B, we invalidate headline B, which invalidates the entire collection of posts and invalidates the entire page. But our navigation or the previews of the other posts or the title or whatever else, they don't need to be regenerated. They stay fresh. So that's a nice mechanism that auto-optimize itself. You need to be aware of the granularity, though. So always make sure that you don't go too fine into detail because there's overhead. Use these auto-invalidating cache keys, so expiry by cache key. And remember the cache limits. So the more caching you add, you risk running into something like your mem cache running out of memory, which actually disables the cache, which doesn't make things faster. Also, caching is a cross-cutting concern. So what does that mean? We have several different layers that our application is usually built out of. And normally we want to keep strictly within the limits of these layers. But some concerns like caching or logging or security, you cannot easily keep these within these limits because they are what is called cross-cutting concerns. So they actually transcend these layers. And that makes them very hard to implement properly. If you do object-oriented programming, for example, it's always a pain to figure out how best to structure these. That is not that you fail to reason about how to best put them into objects. It is because they are inherently problematic because of their nature. So there's 3 ways of dealing with that. And this is important for caching because it means it lets you know how best to implement caching in your application. Through dependency injection, meaning that you can inject a cache object everywhere and then use that cache object. Through decorators, which is a design pattern where you wrap whatever you have with a cached version of itself. That works well if you have interfaces, and then aspect-oriented programming. I'll need to accelerate a bit here. So using dependency injection, that unfortunately creates a lot of noise. So oftentimes that is the least preferable option. The option I usually prefer is using decorators, which means that if a service needs a dependency to execute some work and that work is heavy, we can wrap that dependency with a cached version of itself, and neither the service nor the dependency need to be changed. So you don't need to change their code, you just can wrap them from the outside. And then finally, there's an example of a caching decorator. So here you can see our code without caching, and the naive way of doing the caching would be to immediately include the caching logic with the actual logic of your code. That creates a lot of convoluted mess, unfortunately. So what we want to do instead is have the cache be encapsulated into a separate class. This code didn't need to change. This code didn't need to change. The only thing we changed is in our bootstrapping code, where we assemble our application, we wrap our fragment with a cached fragment. That's the only part that needs to change. The rest of the code, you see, we have the original code again. Aspect-oriented programming, I will not go into detail. It's a method of actually like hook-based programming in WordPress, just at the PHP function level. So you can say, before this function is executed or after this function is executed, do this instead. And this lets you easily wrap all methods with logging or all methods with caching. Now, a last concept here, immediate versus deferred. This, again, like the recency, we have a scale here. We can do something immediately, or we can not do it at all. And there's several steps in between of doing that. And when we think about whether we do something immediately or not, the important part is that the web server is not a task processor. So what I often see is something like this. The checkout, you add action and action and add action to your checkout process or to your form submission, and your web request times out. So that's not the way to do it. The way to do it instead is the checkout just stores the fact that something was ordered, and that's it. And then you have background workers that pick up orders and do the heavy work instead, outside of the web request. With this out-of-process execution, you need to always make sure that you serialize the context correctly, that you can scale the web server and task processor independently, and use optimized infrastructure for the message queue. And then don't preload, pre-instantiate the entire application. So this is normal instantiation. You just execute everything all at the same time. But instead, you can actually use proxy objects. And proxy objects are an approximation of something that's way cheaper to instantiate. And this automatically optimizes everything then. Because when you actually hit a proxy, it turns into the actual object itself, which optimizes by itself. Sorry for rushing through it. This was taking way longer than I expected. Proxies are not always the exact same thing, so be aware of that. Again, granularity is important to consider, and then you can automatically generate proxies with a library called Proxy Manager. And then the last bit, code generation. Code generation means that you turn something from being executed at runtime to executed at compile time, which makes it not be executed at compile time at all, which gets us into the skipped part of the execution scale. And what happens with the opcache is if we do everything, if we compile everything, we get to this, where the opcache is just being read, interpreted, and processed, instead of laxed, parsed, compiled, and so on. And as a bonus, if you keep everything as static as possible, all the static code ends up being this. So static code, it is in memory and is just being executed. So this is the fastest way of doing your logic, because you're mostly not doing the logic at all. So this is it. Sorry for rushing. It was way shorter than I expected.